Hello everyone, this is Dr. Ashok Adhikari. Today I'm going to talk about my work which I'm going to present on IMRC 2026 with International Materials Research 2026 Congress and Symposium F2 and the poster ID is P110. The title of this work is to study the role of the CGS back surface field layer on the performance of two different CIGS solar cells structured through SCAPS software. So starting from the start, the technology of CIGS-based thin solar cells has been making significant progress every day. There are two distinctive structures of CIGS solar cells with and without using the CGS-BSF back surface field layer are modeled using SCAPS simulation. Key properties such as thickness, band gap, and carrier concentration of materials used in CIGS solar cells are mainly simulated and analyzed under the best conditions to get high device performance. These parameters are related to the absorption, transmission phenomenon of photons, and the generation recombination mechanism from the outcomes. The application of the CIGS-BSF layer enhanced the efficiency from 27.31 to 32%. After the experimental parameters of the CIGS are introduced in the SCAPS simulations, the current voltage characteristics of CIGS solar cells are analyzed. The parameters band gap and carrier concentration of CIGS and the CDS thickness have strongly influenced the device performance. The optimum efficiency 20.44 and 28.12 were obtained using experimental parameters of CIGS-340 observer and CGS-20 window samples, which are slightly slower than those of ideal results. Furthermore, the usage of the advanced structure of CIGS solar cells with CGS-BSF layer is very useful in improving the efficiency by absorbing high energy photons and reducing the recombination of generated charge carriers. So in the introduction part, a lot of studies have been performed using SCAPS simulation for designing and optimizing the solar cells, especially CIGS-based solar cells. These research works are related to material property of absorbed materials, properties of window materials, alternative window materials, and the use of order defect compounds at observer window interface, application of BSF layer in observer back contact interface, integration of ultra-lead image, different device structure, CIGS standard solar cells, like CIGS with silicon, CIGS with perovskites, etc. In this simulation, so what we are focused on the use of copper gallium selenide CGS-BSF material is introduced between the CIGS absorber layer and the moving back contact layer in CIGS solar cells. The properties such as thickness, band gap, carrier concentration of absorber layer, window layer, and CIGS layer primarily analyzed and then optimized to find the maximum efficiency as possible. The optimized SCAPS results for CIGS solar cells are compared with and without CGS-BSF layer. Finally, the experimentally obtained parameters are introduced and observe what will be the change, what will be the difference between theoretical parameter and experimental parameters. Therefore, the SCAPS study for the CIGS solar cells offer crucial advantages of precise analysis of critical material parameters and predicts the optimum performance for the structures before heading to the production stage. So in the simulation details, the right and left side we have presented the solar cell structure where we have used the back contact, CGS-BSF layer, CIGS-absorber layer, CGS buffer layer, zinc oxide window layer, zinc oxide and zinc oxide transparent contact oxide, and finally front contact. And in the middle part, we have introduced the table, which is where the parameters are varied, with all the details, the thickness, band gap, and all these parameters which for the respective materials is presented in table 1. So as mentioned, the SCAPS software is carried out in an ideal condition with a working temperature of 300 Kelvin, as well as solar spectrum of AM 1.5G. So in these sections, what we have primarily focused on the variation of the parameter of the CIGS, CDS, and CGS materials. So in the results and discussion sections, in the left side we have presented the CIGS materials. For the figure 2, this is the current voltage diagram, visualize the schematic diagram of the solar cell parameter, open circuit voltage, source current, reflector, and efficiency. The details are while increasing the CIGS thickness. As mentioned, with increasing the thickness, the efficiency also increases. Since with increasing thickness, the absorption process will also increase, and which increases the VOC, and simultaneously cross supply current JSC, and consequently conductor efficiency. And figure 3 is related to the different band gaps, varying the band gaps, and however the band gaps there is some changes with certain range for 1.4 volt. It increases to higher efficiency values, and after that it is decrease. The decrement is related to the decrease in the short circuit current density. Since the where the band gap, the lower will be the absorption of the incident photons. And in respectively, in figure 4 present the curves, and because of the two parameters, the different CIGS concentration. Similarly, what we have here is differences initially the slight increases, and after the 5.10 10 to the power 16, it will reduce to lower value. That the at higher particle concentration, it is due to the natural property, which is slightly it goes to the metallic property, and then the generated charge it generates the recombination sites, so that the generated charge carriers will be combined. So after that, we should focus on the characteristics of the CDS network. So here in this case, thickness and carrier concentration is primarily investigated. However, what we have is the around 50 to 100 nanometer is suitable thickness for CDS, and similarly the more than 10 to the power 17 category is better for this water. For the zinc oxide, however, if we change, there is not very slight changes. Like even though, like since zinc oxide is far from the PM junction of the CDS and CIGS, so that's why this property is not showing any difference in SCAPS simulation. However, the zinc oxide should be the 550 nanometer and more transparent, like similar to the CDS network. After that, we focus on the CDS back surface field layer. So what we have is we have varied thickness from 50 to 400 nanometer, and the carrier concentration similarly vary from 10 to the 13 to 10 to the 19. So from this we have obtained is what we get is the thickness should be lower, means not that much lower, but it should be the around 400 to 500. It's being whatever. If thickness is higher, even though the efficiency increases, the resistance will also increase. So as a result, the figure will decrease. So in this case, it's better to have maintain the lower thickness possible. And similarly, for this case, with increasing the carrier concentration of the back surface field layer, which increases the performance. I think with increasing the concentration, also improve the concentration and reduce the recombination of the charge, general charge carriers. Finally, we have what we have obtained is optimized conditions for the CIGS solar cells without BSF layer. We have VOC 964.5 millivolt and JSC 32.42 percent square, filter 37.31, and the efficiency 27.31. However, with BSF layer, the VOC increases. Here we have 1108.9 millivolt, JSC 33.06 milliampere per square, filter 39, and efficiency is increased to 32.67. I wanted to recall here that the soft liquidation limit for the CIGS solar cell is 33.5%. So what we have, we are reaching almost 33.5%. We are reaching the, which is the value that we have obtained is countable, no? Number is the critical part. So in conclusion, two different structure of CIGS solar cells. We can without BSF layer were effectively modeled using the SCAPS simulation. The simulation study was started with the optimization of matrix properties like thickness, band gap, only for CIGS and calculation of CIGS, CGS oxide, CGS BSF materials used in both the structure of CIGS solar cells. The thickness of materials used in CIGS solar cells can directly impact the key parameters by varying the absorption transmission phenomena of incident photons and the series term resistance of the device. The band gap CIGS adapter can just adjust the number of generated charge carriers. Since the photons have better energy, then the CIGS band gap can be absorbed and participate in the generation recognition process. Moreover, the radial concentration of materials can be helpful in understanding the lifetime and diffusion length of generated charge carriers as well as their recognition mechanism, leading to finding a high quality materials for solar cells. By analyzing these properties through the SCAPS simulation, the solar cells are optimized to obtain the high efficiency. The use of this solar vital is so a vital strategy to enhance the efficiency from 27.31 to 32.67, close to sublimation limit by forming an ohmic contact with the observer layer. So it's finally, and after that we acknowledge the people who have, for example, we are also grateful for the researchers from the Department of Electronics and Information Systems, as Mr. Jain, for distributing the SCAPS software, and similarly the Department of Electrical Engineering Council staff, CCC, and also IMRC for providing us to present our work, and Institute of Physica and the technicians, which are presented in the abstract. So we have also presented some references, and contact if you have anything doubts, you can contact me from these different contact I have put in the ID. So thank you very much for listening and seeing my videos of my work.